Okay, good morning. We continue the lesson today. It's an important topic in complex numbers, so I will give it a title. So that's called the polar form of complex numbers. So when I talk that when I have a complex number, it's a number of this form. It's a plus bi. This form, by the way, is called the Cartesian form. Cartesian form, or sometimes we just say a standard form, yes. So today we want to talk about another way to express a complex number. This might be the first time that we are making something simple more complicated. And the reason becomes clear when we go to the next lesson. But today I just want to tell you, if I give you a complex number in its standard or Cartesian form, what does it mean to write the same complex number in the polar form? And it brings in trigonometry in the problem, yes? So let me just, before doing that, I want to define a concept called the argument of a complex number. So if you have this complex plane, this is the real axis, and this is the imaginary axis. If you find, for example, this point, say this is A, this is B. Okay, so do you remember, I can denote this by a point. I can also denote it, represent it by a vector, which goes from the origin to that point. And then this vector that represents this complex plane makes an angle with the positive part of the real axis. So let me call this angle theta. This is called the argument of this complex number. Yes? So theta is the angle that the vector corresponding to z makes with the positive real axis. This angle is called the argument of my complex number. Okay, so theta is called the argument of z and is denoted by ARGZ. So if someone asks you what is the argument of a complex number, that's an angle. The angle that the vector corresponding to that point in the complex plane makes with the positive part of the real axis. And of course, there are conventions going on. So there are two main conventions here. So one convention is to consider theta to be somewhere between 0 and 2 pi. Yes? 0 included, 2 pi excluded. And that's reasonable, yes? Because if I have an angle, the minimum possible angle is that this point lies on the real axis, the angle becomes 0, and at most it becomes 2 pi. But of course, one of them should be included, the other one should be excluded, otherwise I will be confused. For example, if I tell you if a point is here, I can consider it 0 degrees, or I can consider it 360 degrees. So by convention, we assume that 0 is included and 2 pi is excluded. So if I have a point here, if I ask you what is the argument of this complex number, in principle you can say 0, you can say 2 pi, because it doesn't matter, it remains here, but by convention you say 0, not 2 pi. Yes? This is one convention. Another convention, which I don't know why your book, usually this is the second one is the standard one, of course, but in high school probably 0 to 2 pi is better, but anyway, this is the way that we do it. So it becomes from minus pi to pi. And that's also, so from 0 to 2 pi covers the whole plane. From minus pi to pi also covers the whole plane. So we have two standards, yes? So because if I ask you, where is minus pi? Minus pi is this angle, minus pi. So when I say this is positive direction, you know this is negative direction. When I say negative pi, it means that you are here, but that is excluded. So you start from minus pi, and then you go up to positive pi, which becomes the whole circle again, yes? So we can have two conventions. One convention is that we consider theta between minus pi and pi. One convention is that we consider theta between 0 and 2 pi. And this is more popular, but I think for you it's easier to work with this convention. Sometimes that's not under your control. They just tell you which convention you are supposed to use. So then you need to know what to do, okay? So every now and then I will try to solve some problems with both conventions, okay? And then, by the way, you can also express it in degrees, but let us work with radians. You can say between 0 degrees and 360 degrees, or between minus 180 degrees to 180 degrees. The point is that if you write this or that, it is clear that you are covering the whole range of angles in a plane. Either you can consider it from 0 to 2 pi, which becomes the full circle, or you can consider it from minus pi to pi. Yes, that covers everything. Okay, so let me have some exercise just understanding this concept. So example, determine the argument of each complex number according to the given convention. Okay, so let us consider number one. Let me consider a lot of cases because I want to make sure that you understand this. That's important. It's simple but important. So let me just write z equals to 5. Yes. And let me solve it in both conventions here. So I would say that let us consider the convention minus pi to pi. Let us also consider the convention 0 to 2 pi. Okay, so let us consider both of them. So what you have to do, you have to draw and understand where is the location of this point, which is easy. So that's the real axis, that's the imaginary axis. 5 is here, for example. and you draw the vector, yes? So this is your vector. And then you measure the angle that this vector makes with the positive real part. Okay, so what is the answer? The answer is 0, yes? But in which convention? In both of them. So you see, 0 is acceptable here, 0 is also acceptable here. So in both conventions, the argument of z is 0. So when you want to answer this question, you need to tell me the angle that this black vector makes with the real, positive real part. The angle is 0. Is 0 acceptable in this convention? Yes, because it is somewhere between minus pi and pi. Is 0 acceptable in this convention? Yes, because 0 is included. So the argument in both conventions is 0. Okay, let me just go and calculate the argument of this. So z is equal to 2I. So if I want, so let us consider both conventions, yes? Both conventions. So you need to just draw the real axis and the imaginary axis. And then what is the answer? 2I is somewhere here. Yes, 1 and 2. So this is your vector. And then you have to measure this angle. Clearly this angle is pi over 2. Yes? Is pi over 2 acceptable in this? Yes. Is it acceptable in this? Yes. So the pi over 2 is the argument, regardless of which convention you are using. So yes, the argument of z in this case, in both conventions, argument of z is pi over 2. Yes? Let me go to negative real values. So for example, number 3, let me write z is equal to minus 3. Okay, and let me give them a name. This is convention number 1, this is convention number 2. By the way, let us do it the other way around here, because usually, mostly I would use this one. Convention number 1, convention number 2. Okay, so what you do, you just go to the plane and try to locate this point. This point is minus 3, 1, 2, 3 here, and then you draw this vector. Okay, so this is important now. So this is definitely the angle that you have to consider. But if you express it in the first convention, so convention 1, and then you have convention 2. So in convention 1, what do you write? In convention 1, you have to respect to express an angle between 0 and 2 pi. So this angle is pi. Yes? So what you write in convention 1, you can say that argument of z in convention 1 is pi. So what do you say for this convention? What is this convention then? Again pi, yes? Because pi is also acceptable here. Okay, now let us go to the next part of the axis. So here, so number 4, if I write z equals to minus I, for example. So I go to the plane, minus I is somewhere here. This is your point, minus 1 unit, yes? And then you draw this vector. And now the angle is, so it depends in which convention you are looking to the problem here. If you are looking in the first convention, so this becomes this angle, yes? This is the first convention. So in convention number 1, you have that argument of z is 3 pi over 2. But in convention 2, what do you write? What should I write for convention 2? In convention 2, 3 pi over 2 is not acceptable because 3 pi over 2 is not in that range. You need to tell me an angle in this range that represents this. Yes, so what's that angle in the convention 2?
Minus pi over 2.
It's minus pi over 2, yes? So in convention 2, you should write minus pi over 2. Yes? Okay, now let me give you another one. Number 5, what happens, I have this scenario, for example, z is equal to 1 plus I. So first you need to locate this point again. So the real part is 1, the imaginary part is also 1. So this is the point that you have to locate, and then this is the vector. And this is your angle. So in both conventions, what is the angle? The argument is what? It's clear here. What's the argument? You don't need to calculate anything because that's a square. This length and that length are the same. So that is clearly 45 degrees, yes? And that is pi over 4 in both conventions. Okay, so let me give you some more. Okay, so what you do, number 6, let me, for example, write z is equal to minus 1 plus the square root of 3 times I. Okay, so here what I'm supposed to do, first you need to approximately locate this point. So the real part is negative 1. The imaginary part is the square root of 3, which is a little bit larger than this one. So if this is minus, this is 1 unit. So this is somewhere, for example, a square root of 3. So the point that you have is this. And then this is your vector. Okay, so for example, I hope that you agree, in both conventions the answer is the same, yes? Because this is your angle. This is acceptable in both conventions. So in both conventions, so how should we answer this? So you need to find this angle. The point, it is important to realize that it is always, it's better to do it in this way, more or less you need to understand. You find the smaller angle, this is your theta, this is wanted, but you always concentrate on the acute angle. So for example, let me call it alpha. Then in this triangle, your right tangent of alpha, it becomes opposite side, which is the square root of 3, divided by the length of the adjacent side, which is just 1 unit. Yes? And then you calculate alpha. So this becomes this. You can use your calculator. Alpha is tangent inverse of square root of 3. But of course, this is one of those famous numbers. I have it in my memory. So it is 60 degrees, pi over 3. But be careful, this is just alpha. But we want theta. So theta is pi minus this one, yes? So what you write in both conventions, argument of z is not this angle. Is pi minus pi over 3, which becomes 2 pi over 3. But that is the argument of your complex number. Okay, for example, what happens, let me just write some famous ones. So number 7, for example, what happens if I have minus square root of 3 and then minus 3i? So I want to find the argument of this complex number. So first, again, you have to locate it approximately. So the real part is minus the square root of 3, for example, here. And then the imaginary part is probably here, minus 3. And then if you locate the point, this is your vector. So here it matters which convention you are using. Let us consider convention 1 first. This is the easier one for you probably. So in this convention you need to concentrate on this angle. Yes? Because it should be somewhere between 0 and 2 pi. Again, I recommend you to calculate one of these acute angles first. Okay, so it doesn't matter which one you want to do. And for example, let us concentrate on this one. And I will call it alpha again, but this is what you are supposed to find in the first convention. Always use tangent, always. So tangent alpha becomes the opposite side, which is this length. And this length is equal to that, so it is the square root of 3. Don't write minus the square root of 3. I'm considering about the length, yes? And divided by the adjacent side. The adjacent side is from here to here. The length is 3. And then you put this in the calculator or the table or your memory. That's tangent inverse of that one. This is still one of those famous numbers. I have it in my memory. It is 30 degrees pi over 6. But then alpha is pi over 6. You are supposed to find theta. So theta, in the first convention, convention number 1, theta is this angle. You know that from here to here is 3 pi over 2, but it is smaller than this by amount of alpha, so it is minus pi over 6. So the argument of your complex number in the first convention is equal to what? This number. So if I multiply this by 3, 9 pi, it's 8 pi over 6, and it becomes what? 4 pi over 3. That's the argument. You calculate this by taking the common denominator and simplify. Okay, but if I want to express it in the second convention, I have to go an angle between minus pi and pi. This is not acceptable, yes, because the 4 over 3 times pi is larger than pi. So in the second convention, I cannot say that 4 pi over 3. In the second convention, I have to go the other way around. So that would be my angle in the second convention. But that's also easy, yes? This, first of all, I am going in the opposite direction, so it should be negative. But how much negative? This is 90 degrees, and this I calculated. It's pi over 6. So in the second convention, if you want to write it down, so in the second convention, I would write like this. So this becomes, the argument of z becomes 90 degrees, which is pi over 2, plus alpha, which is pi over 6, but because it is going in the opposite direction, I have to multiply it by a negative sign. And then I calculate this, yes? So this is 3 pi, 4 pi, 2 pi over 3. So it's minus 2 pi over 3. So you see the answers sometimes are different. So if you use the first convention, I will not, the reason that I brought this up, because in some of the exercises in the book, they are using another convention. For me, I will always use the convention between 0 and 2 pi. It's easier for you to understand. But the reason that I talked about the second convention is because in some of the exercises in the book, you also see this convention. And you see that the answers are different. In the second convention, you answer minus 2 pi over 3. In the first convention, you answer 4 pi over 3. I think 4 pi over 3 is very reasonable because it goes from 0 to 2 pi, very standard. But always, you need to make sure that you know you have to start from the positive part and reach to your vector. And it is always easier to calculate this acute angle and always use tangent. And then when you calculated this, then you immediately realize how should you calculate the arguments. Sometimes you have to add something to some famous angle, or sometimes you subtract. Yes, is that clear? And sometimes, of course, these are not famous numbers. Then you have to keep the tangent inverse something. Let me just randomly write something for you here. So number 7, number 8. So for example, let me write z is equal to 2 minus 3i. I want to find the argument of this. Okay? So how should we do that? As before. So we just go to the complex plane. 2 units and 3 units in the negative part. And then you find this point, and this is your vector. Okay, so let me just go in the convention 1, the easier one. In convention 1, be careful. This is your argument, starting from here, going to here. This is the theta that you are supposed to answer in convention 1. Always you have to start from the positive one. And I told you that it is always easier to calculate this angle alpha, and always you use tangent. So what you write tangent of alpha is equal to the opposite side. This length is equal to this length, which is 3 units. Don't write minus 3 units, yes? Divided by the adjacent side, which is 2 units. But this is not among the famous angles. So what you have to do, you have to write alpha is equal tangent inverse of 3 over 2. That's it. Of course, if I ask you to do some approximations, you put this number in the calculator and you get some decimal points. But here you just keep it like that. But be careful, I am looking for theta. So theta is not that angle. So the argument of z is this bigger angle, which is 2 pi minus this angle, because the whole angle is 2 pi, but I should stop alpha units before that. So this becomes minus tangent inverse of 3 over 2. So that is the argument in the first convention, its exact value. If you want to do approximations, you put these numbers in the calculator, you get some approximate value. Okay, but if I want to do the same thing in convention 2, what is the answer? So convention 2, can you tell me what is the answer? In convention 2, you have to go in this direction. So you see that this is exactly your angle, yes? But you cannot say tangent inverse of 3 over 2, because that's a positive one, yes? I just considered the positive values. But when I go in this direction, I have to express negative values, yes? So what you write for convention 2, you would say that argument of z is just simply minus alpha. Yes? So whenever you want to find an argument of a complex number, what you have to do, you have to write it in its standard form and then find it in the plane and then use this trick. Any number that you have follows one of these rules, yes? So in principle, finding the argument of a complex number is easy. So, and I will use this convention between 0 and 2 pi almost all the time. Okay, any questions here? Okay, now we go back to this important topic of the polar form of complex numbers. So what do we mean by polar form? It means writing it using trigonometry, yes. And I told you that this is the first time probably we make something more complicated than it is. Then you will see why it becomes useful in the future, okay? So let us understand this one. This is also very simple, you see. If I have a complex number, z equals to a plus bi. So for example, let us consider that a and b are positive, so this is a, this is b. And then here I have this vector. And this angle theta is the argument of my complex number. Okay? And then from here to here is the distance from this point to the origin. And I told you that, what do I call this? I call it the absolute value, yes? So from here to here is the absolute value of the complex number. So from here to here is the absolute value. And this is common in the context of polar form of complex numbers. They show it with r. So r is the distance from the point to the origin, which is the absolute value. So if I ask you what is a in trigonometric form, that is easy, yes? Because you would say that cosine of theta is the adjacent side, which is a, divided by the hypotenuse, which is absolute value of z, which is r. So from here you realize that a is r cosine theta. Yes? And then if I write the same thing for sine, sine becomes the opposite side, which is b, divided by the hypotenuse, which is r again. But then you realize that b is r sine theta. Now you take these two and put it here and there, yes? What you get is called the polar form of the complex number, yes? So what you do, you can write z is equal to, instead of a, I put r cosine theta, and instead of, so I have b, instead of b I write r sine theta times I. And then r is in common, so I can factor it out. So it becomes cosine theta plus I sine theta. Instead of writing I on the right hand side, I write it on the left hand side. This is called the polar form of your complex number. Yes. This is given in the formula sheet, but I think it's good to remember it. So let me just write. When you want to write the polar form, what do you need? You need two things. You need r, the absolute value of z, and you need theta. What is theta? The argument of z. So you might wonder why I make such a simple, innocent, complex number so complicated. Yes? The reason is that later we have a very important theorem, and that is Demoir's formula. The point is that if I ask you to raise this number to power 100, for example, it becomes very, very hard. But you will see that there is a theorem in complex numbers. If I ask you to raise this one to power 100, it is extremely simple. Yes? Even though this is the same number, But raising it in that form to power 100 is hard because you have to multiply it 100 times or use the binomial theorem. But because of the very specific form that it appears here, it turns out to be extremely simple to raise this to the power 100. So this means that whenever you want to raise a complex number to a very high power, it's important to spend a little bit of time to change the form from the Cartesian form to the polar form, calculate the high power in the polar form, and then switch back to the Cartesian form. Yes? So this you will not understand right now, but we will talk about that next time, okay? But this time you need to learn about what is the meaning of the argument, and then how we can write the complex number in the form of in its polar form, which is actually simple because you already know how to calculate the absolute value. Today you also learn how to calculate the argument. So what you need to do, calculate this and that and put it in the formula. But do not simplify it. Of course, if you simplify it, you get back the Cartesian form. That is not the logic. The logic is to make that simple one a little bit more complicated, and because something nice will happen in the future. Yes. Okay. For example, let us do some of them are still on the board. Let me start everything from scratch. Okay, so exercise, for example, write each number in polar form. Write each z in polar form. Okay, so let me start with a simple one. So I will always use this convention from 0 to 2 pi, okay? Z is equal to, for example, 2. I want to write this in the polar form. So what I need to do, I need two things. I need the absolute value, I need the argument. But that's extremely simple. If I ask you what is the absolute value, R is the absolute value of Z, is absolute value of 2, but of course it is 2. And if I ask you what is the argument, so you need to convince yourself where is Z. Z is somewhere here, and then this is the vector. In the first convention, the angle is 0. So this means that the argument theta is 0. And then be careful, you have to write it in that form. So you write Z is equal to 2 cosine of 0 plus I sine of 0. And you have to keep it in this form, not simplify it, because if you simplify it, you go back. And that's not the point. So I'm making the number 2 so complicated, yes? But that is this. By the way, if I ask you what is cosine of 0, you will say me 1. What is sine of 0 is 0. If you continue and simplify, this becomes 1 plus 0 multiplied by 2, which definitely is 2. But that is not the whole point. The whole point is to write it in this form. This is called the polar form of this complex number. Okay, so let me just do one more here. So let me just write the polar form of the imaginary unit. Z equals to I. I want to write its polar form. So the first thing that I have to do is to calculate the absolute value. But do you remember absolute value of a complex number? How was it defined? So if I have Z equals to A plus BI, absolute value of Z is a square root of A squared plus B squared out, all the time. But it was so simple I didn't use the formula in this case. But for this one you have to use the formula. So this becomes square root of the real part, but there are no real parts here. Yes, and then you have the imaginary part to power 2, which becomes 1. So the absolute value of this complex number is 1. Okay, and then I need to calculate theta, but this is also simple now, yes? Where is I? I is somewhere here. So this angle is 90 degrees. So theta is pi over 2. So what I do, I would write z is equal to r, which is 1, times cosine pi over 2, plus I sine pi over 2. But of course, there is no need to write this 1. So I simply write z is equal to cosine pi over 2, plus I sine pi over 2. So that is the polar form of this complex number. And I emphasize again, you have to stop exactly there. The point is not to simplify, because of course if you simplify, cosine of 90 degrees is 0, sine of 90 degrees is 1. If you really simplify, you get the same result. And that is of course good, because otherwise we will be in trouble. Okay. Just one more example here. So let us just calculate the polar form of this number that you see here, because I don't need to start everything from scratch. So let me write number 3. I want to determine the polar form of this complex number. So the first thing that you have to do is to calculate the absolute value, which is the square root of the real part squared plus the imaginary part squared. But the real part is negative square root of 3 to power 2 becomes positive 3. This becomes positive 9. So it becomes positive 12. And then of course you can use square root of 12, but it is better to write it as 4 times 3, and then the square root of 4 is 2. That's up to you. You can stop right there. So the absolute value of r is the square root of 12. And then we already did this part. So you see, if you want to write this number in the polar form, you have to do this yourself. But we have already done, and I told you that I want to use most of the time the convention 1. In convention 1, the argument was what? First convention, the argument was 4 pi over 3. Yes? So theta is 4 pi over 3. So this means that the complex number that I have is the absolute value, which is 2 square root of 3 multiplied by cosine of 4 pi over 3 plus I sine 4 pi over 3. And that is the polar form of your complex number. So of course in this form it is simpler than this form. But when I want to raise it to high powers, you see that this is very, very simple, but not this one. Okay, just one thing and then we are done. So if I give you the polar form and I ask you to write the Cartesian form, what we do? So for example, this is the polar form. I give you this from the beginning. And I ask you, what is the standard form? What is the Cartesian form of this? Then what I'm supposed to do? To answer the reverse question. So in that case, I have to calculate this and put the numbers in. So what I do, I will do this. For example, assume that I give you this and I ask you what is the original form. Then you have to calculate these. So of course, cosine 4 pi over 3 is not in the table, so you have to use your trigonometric knowledge. So 4 pi over 3 is pi plus pi over 3. And then we had these formulas before. Cosine pi plus pi over 3, it's minus cosine pi over 3. Yes? and then it becomes minus 1/2. And then you calculate the same thing for sine. So this becomes sine pi plus pi over 3. And we already had, this is minus sine of pi over 3. And then this becomes minus square root of 3 over 2. And then you put them back in that equation. So z becomes 2 square root of 3 multiplied by, instead of cosine, I put minus 1/2. And instead of sine, I put minus square root of 3 over 2 times I. And then I multiply this in. When I multiply this in, this 2 and that 2 are cancelled. So it becomes minus square root of 3. And when I multiply this by here, 2 and 2 are cancelled. Square root of 3 times square root of 3 is 3. And this is the answer. And you see this answer is exactly the answer that I started. So, because that's also important to understand. So if you have it in polar form, for some reason you want the original one, this is straightforward. You just calculate things directly and put the numbers in and then multiply. But usually you need to learn how to do it the other way around. So a complex number in the Cartesian form is given. You should know how to write it in the polar form. Yes? Okay, so I think it's a good point to stop here. In the previous announcement, if you see, I have added something. So those I covered in the beginning of the lesson. I don't know why the order of the book is hidden like this. So they talk about how to multiply, add, and divide later. But I started that earlier. So in the previous announcement, there are many things that you can do from the book. Okay, thank you.